Okay, so we're coming up to sort of the final stretch of the class. We've done a lot of really interesting stuff, but physics wouldn't be complete without a discussion of the simple harmonic oscillator. Now, this thing is so important because it turns out that anything that's periodic, including waves, can be modeled as a simple harmonic oscillator. And so what's kind of funny is this little thing, it looks like it's not very useful at first because it's like, okay, I have a pendulum, it's useful. Okay, I have a spring bouncing up back and forth. Okay, what else? Well, it turns out that like molecules and that stuff we talked about earlier, gases and things like that, they're actually waves. They're particles and waves at the same time. They behave that way at a small enough scale. Well, they behave like a simple harmonic oscillator because what they do is matter, it's constantly absorbing and emitting light. And it oscillates at this frequency. So it turns out that this simple harmonic oscillator, it's really important for quantum mechanics. We actually quantize this thing, and then we use it again in quantum field theory. It gets used in all kinds of stuff in physics. So it's very important, and it's going to be, we'll see that we can do a lot more than just representing pendulums and springs as we go through. We can actually weigh a DNA molecule using this method. It's pretty cool. So a DNA molecule weighs so little, you could never hope to put it on a scale and weigh it. But there's a way using the elasticity of the molecule and things like that, you can actually treat it like a simple harmonic oscillator and measure its mass that way. It's really cool. We'll do that example in class later on, sometime in the next couple of lectures. Okay, so just the basic idea that I want to illustrate here, which is what I talked about in lecture last time, is we have this oscillation. It oscillates between two different amplitudes, and we have these turning points. And these turning points are when the amplitude goes from positive to negative. And you could sort of think of it as the place where the acceleration is maximal and the velocity is minimal. And then the velocity reaches a maximum at the center. Okay? So this x max, this maximum displacement from equilibrium, that's the same thing as the amplitude. And then it's minus the amplitude because it goes back and forth between these 2 points. And so really what's going on here is if I stretch the spring out and then it comes back to equilibrium, it doesn't just stop. It keeps going the other way and goes back and forth, because that energy that I gave it, it gets converted into kinetic energy, and then it has inertia. And by virtue of the fact that it has inertia, it has all of its energy in motion. That energy goes and gets converted back into potential energy in the opposite direction. So this sharing of potential energy with kinetic energy is what's at play here. And so pretty soon we're going to write down an energy equation for this because it's easiest to explain it in terms of energy. It makes the most sense. This is just like some basics about frequency and what it means to have an angle, displacement angle. We'll talk about more of this pretty soon. I already talked about some of these slides, so I'm going to kind of go through this a little bit fast. But here's the basics. So we've got this position. If the position is a cosine 2 pi ft, where omega is 2 pi f, then we take the derivative of this, and then we have a minus omega coming out front, and we can simplify that by calling this minus, or this a omega, v max. And then we get this plot, that's the velocity as a function of time. It's just the derivative of the position as a function of time. So the instantaneous velocity is 0 at the turning points because the slope of the position graph is 0. And these are the turning points of the motion. That's an important concept for orbital dynamics. So when I have Earth is in the orbit around the sun, there's turning points for that orbit as well. That orbit is a type of sinusoidal orbit where every year we come back to approximately the same place that we started from after 365.25 days. So we can treat not just, we can treat gravitational interactions in space using simple harmonic oscillator equations as well. Okay, so there's the position. So let's make sure we understand what's going on here. At time t equals 0, well, we can just plug in 0 there, and we have a, because cosine of 0 is 1, so this agrees with our plot. We just have a at that point. And then when t is equal to t, we have 1, which also agrees with the graph, showing one oscillation cycle has been completed. And then as x passes through these points at 1/4 t and 3/4 t, we have 0 for those. So those are the points where it intersects with the axis. Okay? And then make sure when you're doing these calculations for the homework, you're in radian mode. It'll give you errors if you're in degrees when you're doing the simple harmonic oscillator equations. Okay? So these equations do not express different ideas. There's alternative ways of writing the time dependence of a position of an oscillator. We can write it in terms of this Vmax sine of 2 pi t over t, where this is in terms of the period, and then this is in terms of the frequency. And the two are inverses, so either piece of information is fine. Sometimes I'm given the period, and I can write it in terms of the period. Sometimes I'm given the frequency, I can write it in terms of that. Or I can calculate either directly. By knowing one, I know the other. Okay, so let's do an example. Try to write this down really quick, see if you get the right answer. An air track glider is attached to a spring and pulled 20 centimeters to the right and released at time t is equal to 0 seconds, and it makes 15 oscillations in 10 seconds. Okay, what's the period of the oscillation? So the time it makes to take one oscillation. What's the maximum speed? And what's the position and velocity at t is equal to 0.8 seconds? So for part C then, to do that one, you're going to need to write this in terms of a position and velocity function, x of t and v of t, and then plug that in and solve for it. But first, let's deal with each one separately. So try to calculate. So what's the period of that going to look like? Okay, so we can figure it out. We have 15 oscillations in 10 seconds, so we know that the frequency is 1.5 oscillations per second. You see how we just did that? We just said, okay, there's the frequency, and then the period is just the inverse of that. So that means it takes 0.667 seconds to make one oscillation. That's the meaning of the period. Does that make sense how I calculated that to everybody, how we're coming up with that? It's pretty straightforward. Okay, good. All right, so then the amplitude is 2 meters, or no, 0.2 meters. So we've got Vmax is 2 pi times the amplitude over the period. So we know Vmax because we have that formula for Vmax is 2 pi A over T. And remember, it's also A omega. This is also in terms of omega. But period, omega and T are inversely related. Omega is 2 pi times the frequency, and then T is 1 over the frequency. So we just take 2 pi over T, and we plug that in. So that gives us Vmax. Then we use our equation for the simple harmonic oscillator. X is A cosine omega t, or 2 pi little t over big T. And then we have our amplitude, cosine of our 2 pi, the time of 0.8 seconds over the period. And that gives us where the position of the object is located at time is 0.8 seconds. Now what's cool about this formula is if I make 1,000,000 seconds later, this thing is still going to give me the right answer. Okay? Because this thing is not realistic. This does not include friction. This just pretends that the thing never slows down and never experiences friction. So it's just going to bounce back and forth and never stop. Now, there are things in nature that are like this, right? Like a molecule that's some temperature, right? It's oscillating because it just has some energy to vibrate and do what it's doing, okay? Vibrational frequencies of gas molecules, that's a thing. Well, that thing's not, unless that thing runs out of energy, if it just has some fixed energy, it's just going to keep doing that. It's probably oscillating at like millions of times per second. So there's an example of something that kind of behaves like a simple harmonic oscillator and doesn't run out of energy. Now this thing, if it actually had friction, that would be more realistic, and the amplitude would decrease gradually. But for these early examples, we'll just assume there's no friction. So yeah, it just keeps going. Once you have these two functions, x is a cosine omega t, v is minus v sine omega t, v max sine omega t, or minus a omega sine omega t. Once you have those two functions, you know where it is for all of time. It's pretty powerful. So that's the nice thing about simple harmonic motion. Okay, so 0.8 seconds is slightly more than a period, so the glider will have just begun a second oscillation. So it's completed one full oscillation and it's gotten a little bit ways along in its second oscillation. And then, so our calculations agree with what we'd expect, and it makes sense. Okay, now we're going to talk about the most important aspect of this, which is conservation of energy. So, does everybody remember our energy equations? We have kinetic energy and we have potential energy. Kinetic energy is 1/2 mv squared, where v is the velocity of my object. So v is equal to the velocity of my object, and m is the mass. M is equal to the mass. And then there's something kind of cool I can do. Momentum is equal to mass times velocity. But notice that I have a factor of v squared in my kinetic energy. So what if I just squared momentum? What would that look like? Okay, that would look pretty close to kinetic energy, wouldn't it? Because it would be a v squared, but then I'd have an m squared on there. So what I can do is I can just divide by a factor of 2m, and one of my masses cancels out, and then I have kinetic energy exactly, mv squared over 2, okay? Which is exactly what I have here. But then I got to do that on this side here. So kinetic energy is also equal to p squared over 2m. So that's another way to express the kinetic energy of an object. Now, what do we have here? We've got a energy equation, and the energy equation here is balanced here. So we've got a starting energy, 1/2 mv squared plus 1/2 kx squared. That's equal to 1/2 ka squared, which is equal to 1/2 mv max squared. So this is the mechanical energy at any point in the oscillation. And then at maximum displacement, the energy is entirely potential energy. Now I wish I had these springs set up again so I could illustrate this point, this equation right now, because it'd be really nice to do that with an oscillator, but I don't. So you're going to have to use your imagination. But imagine that I pull my spring and I'm still holding my spring and I don't release it. What is the kinetic energy of my spring when I'm holding it, displacing it from equilibrium, but I haven't let it go? What's the kinetic energy? It's 0. Okay. Does this object have any form of energy? Yes. Okay, what's the form of energy, What's the form of energy it has when I have pulled it from equilibrium? Okay, potential energy. And what is causing it to have potential energy? Okay, so what about the spring? What's the thing that gives it the energy? Where does that come from? What's the formula for the spring that gives it the energy? Where does that come from? Okay, so she says there's a force from the spring, okay? It's minus kx, right? And then what I can do is I can look at my units and I can remember that energy has units of work. And work is like the integral of f dx, force times displacement. So what I can do is I can integrate this f dx, have a minus here, and I have a minus integral kx dx, okay? And then that's going to give me, what's the integral? It's going to be, okay, minus 1/2 kx squared. Because we have the integral of x dx is 1/2 x squared. And then I can choose my integral from 0 to some value here, such that I pick whatever my value is, and it's going to be my delta x, because it's going to be my value from some initial to some final. So it's going to be like, we'll say like x equals final to x equals initial. And then that's an expression for my elastic potential energy, 1/2 kx squared. And then I can just absorb the minus sign as part of my result here, so it doesn't matter because we're just talking about the magnitude of the energy here. So we can just do that. And then we have our expression for kinetic energy of a spring. So that's where that comes from, that 1/2 kx squared. And since in these examples, the displacement from equilibrium x is my amplitude, I can just go ahead and replace x with a there. And that gives me my 1/2 ka squared for that expression. Now, this isn't the complete result for how we're going to work this out, because a lot of times we're going to have a situation where at one point we have no kinetic energy, and another point we have all kinetic energy and no potential energy. So let's take a situation. Let me show you how this would work for this equation. So if I have a situation where at one point my oscillator is displaced from equilibrium at time equals 0, that's an energy equation, okay? My energy equation is going to be 1/2 kx squared, or ka squared, where that's the displacement, a is the amplitude, plus 1/2 mv squared, and we'll put initials here by it. That's equal to 1/2 ka final squared plus 1/2 mv final squared. So what that tells me is energy is conserved, so my total energy at one point in time is going to be equal to my energy at a different point in time. So let's choose some interesting cases. For the case at the beginning where I've displaced it from equilibrium and it has no amplitude, or it has an amplitude and has no velocity, this term is 0, and all of my energy that I give it comes in the form of displacing it from equilibrium. So all the energy that this thing could ever possibly have comes from what I give it by displacing it from equilibrium. Then later, at a certain time, it's going to have nothing but kinetic energy. And when is that going to be? Well, that's going to be when I have no amplitude. Because when A is 0, as the spring comes back to its equilibrium point, A is 0, so this term goes away and this term goes away, and all of my energy is in the form of kinetic. So now we can understand when this system, this oscillator, has no potential energy and all of its energy is in the form of the kinetic energy. It's when the oscillator has come back to equilibrium. But when it comes back to equilibrium, it has all this kinetic energy. It's going at a maximum velocity. So it's not going to stop. It's going to keep going. And what happens is it keeps going, and all that kinetic energy gets brought to a stop and gets stored again as potential energy, but with the opposite amplitude. So it comes back around, and now it has all potential energy, but on this side. And then the process repeats. back and forth again. Okay? So it's not so complicated when you see it broken down like that. Okay, so any pair of those equations can be useful depending on what you have. You can solve for the speed at any point by knowing the amplitude and the spring constant and the displacement, x. And you can use more things to solve for omega as well. And then here we have a plot showing the energy of the system as a function of time. So you can see at some point, at time is 0, all the energy is potential energy, and none of the energy is kinetic. Then they come like this and they intersect. At a point, there's a specific point where the kinetic and the potential energy are equal to each other. They share energy equally. Then they split, and the energy goes all from being purely in the kinetic energy and no potential energy. That's when it's going through the midway point. And then it rises back up again as it comes to a stop, and it's all potential again. And then it repeats. And what's cool about this is, if you see that, the function that describes the relationship of the energy of the system as a function of time is also a sinusoidal function. It's also sines and cosines. So it's not just the position and the velocity, it's also the sines and it's also the energy that obeys that relationship as well. And notice that both K and U oscillate twice each period. Can you understand why they oscillate twice each period? What that means is that the energy is shared and distributed between the system twice in one period. So it goes from being all kinetic twice. It happens here when it crosses the equilibrium point here, and here as it's coming back. And then it goes to being all potential energy at two different points. Here, as I've displaced it from equilibrium before I've released it, and here, when it's come back through the equilibrium point and again is stored as kinetic energy, or no, as potential energy. So those are the 2 points where it's got either all kinetic or all potential. And then the halfway points between there, it's shared evenly. And some fraction of those two at other various points throughout the cycle. Okay. So there we go. All right, so let's do another example. We've got a 500-gram block on a spring, and it's pulled a distance of 20 centimeters and released. The subsequent oscillations are measured to have a period of 0.8 seconds. At what position or positions is the block's speed 1 meter per second, and what is the spring constant? Okay, write this down on a sheet of paper and see if you can figure out how to solve for it really quick, based off of the equations that we just went over. And then we'll go over the solution. Okay, so the block starts from the point of maximum displacement, where the energy is 1/2 Ka squared. It's all kinetic, or all potential energy. Sorry, keep saying that again. It's all potential energy. At a later time, when the position is x and the speed is v, the energy conservation requires that it's going to be 1/2 mv squared plus 1/2 kx squared is equal to 1/2 Ka squared. Now, what they mean by this term here, where it's kx squared, it doesn't mean that it's at the full x displacement. It's just some displacement from equilibrium. So in that second term there, that 1/2 kx squared, if x equals a, right, then that term is going to be what? If x equals a. The term's going to be 0, right? So we have to remember, what does that correspond to? We have to have a situation here. This term cannot be equal to a here, or else this equation doesn't work. So remember that this is for the special case when we have x not equal to a. And then we can solve for x, and we can see that x is equal to this a squared, the amplitude, minus this kinetic term divided by k. So then we have this interesting expression for x, and it tells us where we can expect to see the displacement. So for part A, it turns out to be a little more complicated to solve than you might have thought. Because you see here, we talked about, okay, what position or positions is the block speed equal to 1 meter per second? Okay, so we're solving for the position where it's 1 meter per second, and then we have k over m is equal to omega squared. So we have this angular frequency, and then we have to solve for this. We know it's 1 meter per second, but we had to solve for omega, and then we know that the amplitude is 0.2 meters, so that tells us where. So solving for where something is equal to a velocity, that's where things get a little bit tricky. So make sure you review this. It's not a super simple calculation, but it's totally doable if you know how to use this equation correctly. Okay, so that tells us that there's 2 points where this is the case. It's at plus and minus 15 centimeters. Okay, there's 2 positions because the block has this speed on either side of its equilibrium. And then part B is easier. We just know that the period is 2 pi f, but we know what 2 pi square root of m over k. And where does that come from? Who can tell me where that comes from? Somebody. Where's this relationship for the period come from? What is the period? So period is equal to 1 over frequency, right? So let's see here. So we have t is equal to 1 over f, and then omega is equal to 2 pi times f. So if I have 1 over omega, then I have 1 over 2 pi f, right? But then I have to divide by 2 pi here to be consistent. So then I can bring it over to this side to cancel it out. So I have a 2 pi up here, and then I have to solve for this omega, and that's where it comes from. So it's square root of m over k, and k is equal to 4 pi squared m over the period squared. So make sure you review that, because it seems easy, but it's easy to make that mistake and get confused on this. Okay? So we have our value of 31 newtons per meter. That's the spring constant that we solve for. And so it's consistent with the observation that the block oscillates fairly slowly. So what this spring constant does is it's sort of units of force per meter. It's the amount of force I have per meter. So the more stronger my spring constant is, the more force I can put into my system. And then the more force I can put into my system, the more energy I can put into my system. So if I want to make a very powerful, energetic system where the block can oscillate very fast or can exert a projectile with a lot of force if the spring is going to hit something, like if it's a spring gun or something, I'm going to want a really strong force constant, a really large force constant, which is a further illustration of the force that I can put into the system going into and contributing to the energy that the system can store. So the more force, and there's another way to think about that too. If I use more force when I pull the spring back, I can pull the spring further, and then there's more energy. So even as it oscillates and the period doesn't change, it goes out to a further distance because it can store more kinetic and potential energy. It's just that because of the way that the simple harmonic oscillator works, the balance is such that the period never changes. Question? Sure. Okay. Okay. What position or positions is the block speed 1 meters per second? Yes. Okay, sure. So we've got this relationship between omega. We have K over M is equal to omega squared for a simple harmonic oscillator. So if K over M is equal to omega squared, right? This K over M is equal to omega squared, then we can write this as the inverse of each other because we have M over K. So what we're going to do is we're going to write K over M, and then we already have a factor of V squared. So we keep V in the numerator. We square that, and then we do M over K is 1 over omega. So we just do, I should say it's 1 over omega squared. So yeah, so then it's just V over M, or V over omega, and both of them are squared. Do you see how I did that? I took the inverse relationship. K over M is equal to omega squared. That means that M over K is equal to 1 over omega squared. And then you can just factor that. Do you see that? Okay, cool. Yeah. So it's a little bit of understanding the definitions and a little bit of algebra. Play around with that. Okay? All right. So now we have a conceptual question. Let's see about this one. Let's try this one out. So there's 4 springs that have been compressed from their equilibrium position at x equals 0. When released, the attached mass will start to oscillate. So rank them in order from lowest to highest, the maximum speeds of the masses. So here's the different speeds. So how are we going to calculate this? What's the formula we're going to use for, but remember, we went over that formula here. What's our little relationship for V in terms of omega and K, right? We've got this little relationship here. So we can plug in these different values of these masses and these spring constants to figure out what V max is going to be. Okay? So C is bigger than B, is bigger than A, is equal to D. So A and D are equal to each other. And that comes from energy conservation. So we use this 1/2 Ka squared. That's equal to 1/2 mV max squared. And that gives us V max, which is equal to square root of K over MA. Okay, so the formula that we use, we can make a little table of this, right? We say, okay, we've got V max, make this bigger. V max is equal to square root of K over MA. Okay, let's make our table for our different masses and figure out what this is. So we've got V max is equal to square root of K over M. All right, so let's see. Okay, so we've got our first one. So the first one is A. We've got, so for A, we've got V max. So we've got A, we've got V max. What's that going to be equal to? Sorry, I'll do it like this. We'll do V max in the column. We'll do V max, and then we'll do A, B, C, and then is there, I think there's a D. Yeah, D. Okay, great. So, V max like this. Okay, so, and we know V max is square root of K over MA. So the first one has a value of K, and it's 4M. So it's going to be an A is, it looks like So the 4 springs have been compressed from their equilibrium position at x equals 10. When released, the attached mass will start to oscillate. Rank in order. Okay, so I think what they're saying here is the amplitude of this is minus 10 centimeters, right? For the first one, or 10 centimeters. So we've got an amplitude of 10 centimeters. So we've got V max is going to be equal to 10, and then it's square root of, and then we have K over 4m. K over 4m. And then for B, it's going to be 1/2 K. So we're going to have square root of 1/2 over 4m. So it's 1/2 K divided by 4m. And then it's going to have a displacement of only, let's see. Okay, so there's 0. Oh, I see. It's going this way. Okay, so we're going this way. So it's 5, 10. Okay, then here it's 5, 10, 15, 20. So here we have 20 from equilibrium. So we have a 20 in front, whereas the first one we had 5, 10. Okay? So we're going to compare these two values. Okay? We're going to have fractions with fractions. So this is going to be 1 over 8m square root, and we have a k, square root k over m. So it's going to be 1 over root 2. So we're going to have square root of k over m. And then I had a half because I had a root 2 over here. So that just becomes 5k over m. And then we're going to have square root. So we're going to have 4 root 2. Okay? So we have 20 over 4. So 5. But then there's a root 2. So we have a 2 here. Okay? Left over. And then for C, it's 5, 10, 15, 20. Okay? 20. And then we're going to have square root of, let's see, k over 2m. K over 2m. And then finally, D, it's only 5. The amplitude is 5. And then it's square root of k over m. Okay. Square root of k over m. So then, let's take a look at our ranking and see if we got this right. So C is bigger than B. A and D are equal. 5 square root of k over m. 5 square root of k over m. Okay? Yeah. And then there we go. So we've got C is greater than B is equal to A and D. There we go. Okay. Does everybody see how I got that? Yes. We don't have to use meters because we were consistent with our units. And we didn't have to convert anything. We got lucky. But yes, technically you could put, convert this into meters and just put a little, but it wouldn't change our result. Yeah. Yes. For A, how did I get 5? So what did it start out as before I simplified it? What's the formula? We had square root of k over ma. Okay, so let's look at A here. So A it's been pressed in 10, right? So its amplitude is 10. So we have V max for A, that's 10. And then square root of, it was K over 4M. But what do? I can factor this. So this is the same thing as 10 times square root of K over M times square root of 1 over 4, and then that's 1/2. So I just divide that, and that just becomes 5 square root K over M. Okay? So that's how I got that. All right. Great. So we did that one. Now, we talked about pendulums already. It's an oscillator where we displace it from equilibrium and it swings back and forth. It has an arc length S that's analogous to the position X of a horizontal oscillator. The pendulum is in equilibrium at S equals 0 when it hangs straight down, and the arc length and the corresponding angle theta are positive when the pendulum is to the right of the center and negative when it is to the left. So here we have a picture. Now, what is this? This is a force body diagram or a free body diagram of our pendulum at a given point. Notice there's a tension. That's the tension from the string. Then there's the weight downwards. And then we have, the weight has a tangential component minus mg sine theta. And it also has a downward component. So don't get too confused. They broke that weight up into two components. That force body diagram is really badly done because they broke that second vector up into two different pieces, but it's really just all part of that vector. That W, WR is the projection of W along this y-axis and this x-axis. And they went and did a tilted axis, but they didn't warn you that they did a tilted axis. So sometimes when you have an object that's tilted, right, you can do a tilted axis, and you can call the tilted axis like y, even though it's actually not. And the whole purpose of that is then you don't have to break up your weight into its x and y components. Or you only have to break up your weight into its x and y components. But they should have said that there. They didn't explain. Does that make sense to everybody what they did there and what they're communicating? Okay, so nobody's confused by that. Because I agree, it's not the best way to write that. But if you look carefully on your slides, you will notice that these little WR and WS are light red, not dark red. The actual two force vectors in this figure are T and W. Those are the only two actual vectors. Okay, cool. So and then they break W up into its components. It's an oscillator, but its motion is not simple harmonic. If you take it out to a certain point, it's no longer simple harmonic oscillator. And neither was those springs. George was telling me, oh, it was falling, the weight was falling off because you're only supposed to displace it a small amount. If you displace it more than a small amount, it kicks it out and it's got inertia, the weight keeps going and slides off of it. So these equations for treating pendulums as simple harmonic oscillators, they're only valid at small angles. At large angles, the pendulum deviates from a simple harmonic oscillator. But for small angles, you can see that the free body diagram shows the two forces act on the pendulum. We've got the string tension and the weight. The restoring force is the component of the net force that's tangent to the arc in the S direction, and the force components are perpendicular to the arc, and they affect the string tension but don't play a role in returning the mass to equilibrium. And you can see that the tension is always perpendicular to the arc, so the restoring force is the tangential component of the weight. So here we go. We have our force. That's the tangential component of the weight. And then they have a nice little drawing here that shows the geometry of the pendulum oscillations. And then there you go. So then the next slide, we have it going over. So the restoring force on the pendulum is not directly proportional to S and thus not a linear restoring force. So in general, the oscillations are not simple harmonic motion, but it can be approximated as that for very small angles. So it says that there. So anything that we do in this class, just assume it's for small angles. We won't worry about bigger angles where it's not the case. Okay, so we have these approximations of sine of a small angle. It's very close to 0.1, and cosine of a small angle is very close to 1. So we use these a lot in physics, actually, these little small angle approximations. Sine of a small angle being like close to 0.1, and cosine of a small angle just being 1. Okay, so we get pretty close to within 0.5% for small angles. And so you can use the small angle approximations for angles of up to about 10 degrees. Assume they're all small angles. I promise you I will not put anything on the exam that it's not small angles. They all will be. And then we can use this. We can replace sine of theta by theta, which is equal to S over L. And then we get a simpler restoring force of minus mg theta. And then it simplifies to minus mg S, which is the arc length, over L, which is equal to minus mg over L times S. So for small angle oscillations, the restoring force on the pendulum is linear and directly proportional to the displacement S. And so the small angle oscillations of the pendulum are simple harmonic motion. And then we can deduce the frequency and the period if we compare from our earlier equation in our restoring force of Fx equals minus Kx. We can see that for a pendulum, the quantity mg over L plays the role of the spring constant K. And we simply need to substitute mg over L for K in the earlier equations for frequency and period to see that for a simple pendulum, omega, which is 2 pi f, is equal to square root of g. That's gravitational acceleration, 9.8. If you're on a different planet, it's going to be different than that, over L. Frequency is 1 over 2 pi times square root of g over L. And the period is 2 pi, the inverse of that. Okay, so that's everything I wanted to say for today. Anybody have any questions? Okay, I'll see everybody on Wednesday. And then on Friday, we have our midterm.